Welcome back to the Math Professors. If you enjoy content that can be found in any college math class, please consider liking, subscribing, and sharing. I'm Professor Van Hammond. I'm going to do some Taylor series for the sine and cosine function. So really I'm going to do the Maclaurin series. It's a little quicker. They're very similar. So the Maclaurin series is just a Taylor series centered at 0. So let's get started. So f of x is going to be equal to the sine of x. I'm going to need all the derivatives in, and then see if there's going to be some pattern here. So what we know is for that Taylor series, we have to find these coefficients. And right now I'm just going to start the numerators of these coefficients, and we'll worry about the factorials and the end of that power in a second. So we're going to see some pattern here. Well, the derivative of the sine of x is the cosine of x. The derivative of the cosine of x is minus sine of x. The derivative of negative sine of x is minus cosine of x. And I can see that we're starting to get a pattern here. So the derivative of minus cosine of x is going to be, well, minus the minus sign. So sine of x, and then cosine of x, and then minus sine of x, and then minus cosine of x. And you can see that this is cyclic. It's just going to continue to repeat, repeat, and repeat. So dot, dot, dot. Your goal really is to find, the nth of x. Now, the problem is I got two different functions here. So the 0th derivative, the 2nd derivative, the 4th derivative, the 6th derivative, we can see that all the even derivatives is going to give me a sine function, so we have to do it in 2 steps. Your trig functions, you're going to have to do your even derivatives, and you're also going to have to do your odd derivatives. Well, the evens are going to give us sine functions, and the odds are going to give us cosine functions. Now we can also see that, sine, negative sine, sine, negative sine, sine, negative sine, that this is going to alternate, so this is going to have to be negative 1 to the n times the sine of x. And then very similar for the cosine of x. This is going to be negative 1 to the n times the cosine of x. So remember, if I want to do the Maclaurin series, I have to evaluate these things at 0. So f of 0 is going to be the sine of 0, which is going to be 0. F prime of 0 is going to be the cosine of 0, which is going to be 1. And then you can see that this is just going to bounce back and forth between zeros and ones. Well, we have to be careful. That's not exactly true because this is going to be negative 1. So, and then positive 1, and then 0, and then negative 1, and so on, because remember the Dacon thing alternates. But I can tell that all the sine functions, this is going to be the eventh derivative of 0 is going to be 0. And then the odd one? Okay, we're going with that. I can't say it. The odd, nice, of 0 is going to be minus 1 to the n. Because the cosine of 0 is just going to be 1. So setting this up, now what we have for our Maclaurin series is going to be equal to, well, this will be 0 plus 1x plus 0 over 2 factorial x squared plus a negative 1 over 3 factorial x cubed plus 0 over 4 factorial x to the 4th plus dot, dot, dot. And now this splits. Remember that we're going to have f to the 2n of 0 all over 2n factorial x to the 2n plus f of 2n plus 1 0 all over 2n plus 1 factorial x to the 2n plus 1 plus dot, dot, dot. Now, again, the even ones were 0, and the odd ones were actually alternating this negative 1 to the n. So, simplifying this, we have x plus, minus x cubed over 3 plus x, hopefully factorial, plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus x to the 9th over 9 factorial. I think we get it. Plus dot, dot, dot. We have plus the negative 1 to the n all over 2n plus 1 factorial x to the 2n plus 1. So what I like about this is sine's an odd function. You can see that all the odd powers are remaining, and so this is equal to our sine of x, which really can write as the summation from n equals 0 to infinity of minus 1 to the n, x to the 2n plus 1 all over our 2n plus 1 factorial. Now, what's really cool about this is, remember, we just did one with the hyperbolic sine function. The hyperbolic sine of x was actually this exact same thing, except it didn't alternate. So it was just this without that negative 1 to the n. So this was equal to the summation from n equals 0 to infinity of just x to the 2n plus 1 all over 2n plus 1 factorial, which is cool. Now, very similar for the cosine and the hyperbolic cosine. You know, we know this is going to do a very similar pattern, that the cosine of x, this will be 1, this will be 0, this will be negative 1, this will be 0, and it's going to flip that. So this is going to be 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus, and then so on. So we know that this is going to be equal to the summation from n equals 0 to infinity of negative 1 to the n times x to the 2n all over 2n factorial. And then very similarly, the hyperbolic cosine was the same thing, except it didn't alternate. So what I really enjoy about that is we call them, you know, sines and cosine, hyperbolic sines, hyperbolic cosines, and you can really nail their relationship. That, boy, they are really similar, aren't they? So if you like the content, please consider liking, subscribing, and sharing.